Hi guys, can you hear me?
Yes, sir.
Yes, sir.
Yeah. Who else? Who is missing? Some third guy.
Jishnu Prabhu, sir.
Okay. Smart guy is missing, is it? You all are smart. Yeah, don't worry. I'll just kid around a lot. So what are we supposed to study today? You guys tell me. Which chapter?
Magnetic effects of electric current.
Magnetic effects of electric current. So we studied magnetism. Huh? See, right now we are not having. We are having something weird. Okay, I'm sorry about that. See, right now we are in online class, so there will be some of the examples which I won't be able to show you. But definitely when we are having offline class, I'll just try to give it to you. I'll just try to show you animations there, okay? Will that work? And please let me know if there are some examples which you are not able to understand, because in magnetic effect of current or in magnetism, there are a lot of things which, or lot of properties, or what we can say, a lot of concepts which we need to visualize it. Physics is all about visualization, right? So I won't be able to give you a proper diagram, but I'll just try to show you animations. So please let me know if something is not clear to you, okay? Okay, Atish, and who is that?
Yes, sir.
Sanjay.
Yes, sir.
Okay, Sanjay. Okay, just let me join meeting from my another device so that I can show you some of the examples. Okay, just give me a moment. I'll share the screen. Let me know if you are able to see the screen. Okay. If you're not, please let me know that.
Recording in progress.
Now is it okay? Are we still? Is my audio clear now? Is it?
Yes, sir.
Are you hearing any echo right now?
Yes,
Is there any?
No,
Is there? Tell me. Is there any echo?
No, sir.
Okay, so that's what I wanted to hear. I'm really sorry about that. Okay. So, okay, well, I'll share my screen. Let me know if you guys are able to see. Can you see the screen?
yes, sir.
Yes, sir.
Okay, so we'll be studying magnetic effect of current. Just a minute, guys. There are quite a few things I need to keep in order. Just let me check. See, magnetic effect, before we study the magnetic effect of current, we must know what is magnetism. Have you studied about magnetism? What is magnetism? Huh? What is magnetism? Tell me. What do you understand from the term magnetism? Yes, sir. Mr. Sanjay, sir. What is magnetism, sir?
Magnets connect with each other.
Magnets connected with each other, is it?
The force exerted by the magnet.
See, magnetism, it's a property. Okay, it's a property. Magnetism is a force exerted by magnets. All right, the force we have studied. You have studied about forces, right? Have you or not?
Yes, sir.
Yeah. So that's what magnetism is. So magnetism. Before I start magnetic effect, let's get a few things clear about magnets. Okay, first, See, magnets, when we are saying magnets, there can be natural magnets, right? Natural or man-made magnets, right? Two types of magnet can be there, isn't it? Everything can be of two types. Either it can be, available in nature, or it can be made by us humans, right? So the natural magnet, it was discovered a long back. Okay, I don't exactly remember the year. Let me just check it and I'll tell you. Okay. Okay, so I don't exactly know, but see, the natural magnet was called lodestone. Lodestone. Okay, lodestone is just. I'm really sorry. Can you see my video? Can you guys see my video?
No, sir.
Okay. Okay, all right. See, lodestone, it's just natural stone, it natural occurring stone. It's nothing fancy, but it's a stone which shows magnetic property. What is magnetic property? That means magnetic force. Okay. When we are saying magnetic property, that means magnetic force. That means what type of force a magnet can have? Huh? Yes, sir. What kind of force magnet can have?
Magnetic force.
Means attracting or repulsive force, right?
Mm.
Either the magnet attract or it can repel, isn't it?
Yes.
Right? Yes or no? That's magnetic force. Means, yeah, obviously magnetic force can have two effects. Either it can attract or it can repel. Okay. So the lodestone shows this type of property. Lodestone shows this property. That's why it's called naturally occurring magnet. And it was found long back. I don't exactly remember, but around 800 or 900 BC. Okay. So that time itself, we have discovered that there is some stone which shows magnetic property. Okay, that means magnetic force. Now, man-made magnets, it can be, again, and it is always a permanent magnet. Okay, we have to understand this. This natural occurring magnet was a permanent magnet. Okay, now man-made magnets can be either, it can be a permanent magnet. Okay, or it can be what? What? Permanent and? Yes, sir.
Non-permanent.
Please tell me, permanent and?
Non-permanent.
Non-permanent.
Temporary, yeah.
Temporary.
Right? Temporary magnet. Okay, now in permanent magnets, how we made permanent magnets? So, what we did, we found some of the materials that shows magnetic property. Okay, that was our iron, nickel, and cobalt. There are others, but these are the major, and these materials we can find really easily. Okay, we did, we iron or steel, we say steel is just carbonated iron. When we add carbon in iron, that we call steel. Okay, so when you hear steel, that means it's a strong iron. Okay, when iron plus carbon, this is called your steel. Of course, the major ingredient is your iron. Okay, so cobalt. So what we did, we melt it, and then we pour in some shape. That means we mold it. First we melt it, then we mold it. Okay, in some shape. like some shapes you are aware of this bar magnet, right? North pole, South pole, right? Isn't it? Bar magnet or horseshoe magnet. You must have heard about that, right? These type of magnets, isn't it? Yes, sir, or
Yes,
no,
sir.
sir?
Yes, yes, yes.
Just give me a minute. Hello? Hello? In class, I'm in class. Yeah, I'll call you. Bye. I'm sorry. Sorry. So this can be molded in some different shape. And then what we do after this, we keep this. Let's say you made this bar magnet. Now you keep this magnet in a strong magnetic field. Okay. In a really strong magnetic field. So this arrow represents magnetic field, B. Magnetic field is represented by B. Since it's a vector quantity, I'm going to write B vector. Okay. It doesn't mean this arrow doesn't mean if I'm making arrow like this, it doesn't mean I'll write like that. Okay. It just means I'll be writing like this, or you can put a minus sign here if you want. Understood? So please don't get confused. Okay. I'm sorry. I think this one. So when you pass a strong magnetic field from here, okay, when you are passing a strong magnetic field, what it will do, it will magnetize, it will charge the shape of this, charge the structure. Like suppose the magnet, this is some material, okay, this is a magnet. It's not a very strong magnet. When you pass electric or magnetic field through it, or when you keep it in an electric or magnetic field, what will happen? It will get charged, means the atom, means all the individual atoms will be magnetized. Okay, that means it will show magnetic property. So inside a magnet, so this is a magnet. Okay, the entire atom is north south. Okay, north south, like this, north south. You can also draw in different shape, it doesn't matter, north south, because since we are aware of bar magnet, that's why I'm just drawing bar magnet. Okay, inside. So all the atoms you see, it is north south, it is like that. That's why if you have a magnet, let's say you have a magnet north pole, south pole, if you break the magnet from here, what will happen? Two magnets will be created, both will have this pole, north south. Got it? So you are breaking it from here. Understood? Till now, whatever I have said, you understood. And this process is called powder metallurgy. Okay, this process is called powder metallurgy. Please check the spelling of metallurgy. I'm not sure whether it is correct. Okay, so powder metallurgy, the name of process is, but it's fine. If I'm just telling you how we make permanent magnets. And how do we make temporary magnets? What we do, we just wrap the coils. Okay, we wrap coils in some shape. Okay, like this shape, or sometime in circular shape, or in different shape. And then what we do, we pass current through it. When we pass current through it, it will behave as a magnet. Okay, it will behave as a magnet. Okay, these lines represent the magnetic field lines. Okay, this is magnetic field lines, nothing fancy. We will study about these things. Okay, so some of the temporary magnets are your solenoid. Okay, solenoid is a temporary magnet, like electromagnets. Okay, these are called electromagnets or solenoids. See, what's the difference between electromagnet and solenoid is just, it's a very simple difference. See, if this is a solenoid, if we just add a soft iron core inside, if you put an iron bar or iron cylindrical material, this will be called electromagnet. Okay, that's the only difference between solenoid and an electromagnet. Understood? Yes or no?
Yes,
Are
sir.
you there? See, if you guys won't reply, I'll just end the class. Okay, because I need it should feel like me that I'm teaching someone. If you won't reply, I'll just end the class. Okay, I won't ask it again. Atisha and
Okay, sir.
Sanjay, both of you. See, if you have any doubt, you can clarify your doubts here, right? Don't wait for your exam so that when exams come, you'll start studying and you'll clarify your doubt. That time you might not be having anyone to clarify your doubt. Okay, so pay attention. It's see, these are the things not they are not going to ask in exam. But before you study about magnetic effect of current, okay, so before that you should know what magnetism means, or what is magnet. So I have explained you about magnets here, so temporary and permanent magnets. So can you give me some of the examples of permanent magnet? Tell me some of the examples of permanent magnet. Yes.
Sir, like, you're asking the shape or materials.
Just tell me.
Sir, iron, nickel, cobalt.
Can any one of you tell me what permanent magnet example? Give me one example of permanent magnet.
Naturally occurring magnets.
So that, no, dude, that is not example of permanent magnet. What is the use? Okay, I'm sorry, my mistake. I should write use of permanent magnet. My mistake it was. Use of permanent magnet. Yes.
Headphones.
Motors. Where do we use permanent magnet?
In headphones and audio speakers.
See, can you see a fan in your home? So how the coil of your fan rotate? It is made of what? It is made of what? Motor, induction motor.
Yes, sir. Induction.
Right? Induction motor. And this induction motor, inside it, there are magnets.
Sir, MR is fine.
Okay, like it is there usually in fan, it is of cylindrical shape, something like that. And there will be magnets fixed here. Okay. Understood? So this is the magnetic field line, which will help this magnet. And when you pass current through it, it will, from electrical energy, it will convert to mechanical rotation. Okay, mechanical energy, or you can say. So induction motor is one of the use of permanent magnets. Permanent magnets can be used to create temporary magnets, right? How? Have you ever seen a permanent magnet? Let's say this is a permanent magnet, a bar magnet, okay? North, south. Why, by the way, why it is called permanent magnet and why it is called temporary magnet? We are again going to see that. The thing is, see, its magnetic property do not changes suddenly. You know, it do not degrade with time. It will degrade in long period of time. Like if you have a permanent magnet, it will remain magnet for a really long period of time. That means it will show magnetic property for really long period, like 100 years or 200 years maybe. Okay, or depending upon the strength, how much strength it is. Okay, temporary magnet, you can just switch off the current and it will just be a metal. It will not be a magnet. Okay, so when you're passing current through a temporary magnet, that's when it behaves like a magnet. When you remove current, it will not be a magnet at all. That's why it is called temporary magnet. But temporary magnets are really strong magnets because it depends. We'll study about that. Okay, don't worry, we'll study. Now again, let's say second example that I'm trying to give you here is, let's say here you have this north pole, south pole. Now if you keep some nails, so what you will see, some nails will just get cluttered over here like this. Okay, some nails, it will just stick to it, you'll see. And again, these nails, these will again attract some of the nails, right? These nails will again attract some of the nails. That means what? See, this nail is not a magnet. This nail, not magnet, right? These nails are not magnets, but it is attracting. See, it is holding up this another nail. That means it is behaving like a magnet, right?
Yes, sir.
So what happens? These magnets, this magnet will magnetize these nails. Obviously temporarily. Okay. When you detach this magnet, then again this will get detached here, detached here. Okay. So that is again one, how you can clear. These are also called temporary magnets. Okay. So temporary magnet doesn't mean you always need to pass electric current through it. Okay. So here it is kind of temporary magnet. These nails will behave like a temporary magnet, and the strength will also decrease. Like the nails attached to this bar magnet. See, there are 3 nails attached. Maybe these nails will be able to attach only 2 nails, and these 2 nails may be able to attach only 1 nail. Okay, so the strength will gradually decrease, obviously. All right. Now, what is the use of temporary magnet? Tell me one use of temporary magnet. Temporary magnet means, let's say, electromagnet.
So in
Yeah.
batteries.
Yes, tell me, sir.
So, in that also can be used in motors.
Yeah, actually, but have you heard of bullet trains?
Yes, sir. Maglevs.
Yes, very good. Maglev train. What is the meaning of maglev?
Magnetic levitation.
Yes, magnetic. See, this mag means magnetic,
This levitation.
and this is levitation, of course. Right? Magnetic. What do you mean by magnetic levitation? Yeah. See, I'll just try to explain it here. Okay. See, suppose this is your train, bullet train. Let's say this is your train. Now this surface, the bottom surface, let's say it is made such that this is your north pole, okay, of the magnet. And on the tracks, let's say this black line, these tracks, in these tracks, you'll passing electric current. Okay, you'll be passing current through this track. What will happen? It will create another north pole. So north pole will repel each other, right?
Yes, sir. Yes, sir.
Repel each other, and the train will lift in air.
So how do they balance it from going left or right, sir?
Yeah. So now there is another set of magnets that attract that pushes it this side or this side. Again, that depends upon which direction we are passing the current. So this is one set of magnet which will lift the train. Another set of magnet will push the train. Okay. Magnet means, obviously we are talking about electromagnets. Okay, in which we are passing current. See, the thing is, magnetic field, the direction can be changed by changing the direction of current that we are going to study. So this is all about your magnetism or magnets. Okay. So the first part was magnet. I think we have covered enough about magnets, right? So is this clear to you all? Yes. Magnets, right? Just give me a minute. So now we are going to study about the electric means when we are passing electric current through a coil, what happens? What will happen? Okay, so that effect we are going to study. Just give me a minute. See, in I think 1802, there was a mathematician or a physicist, I don't exactly remember, Gian. Okay, full name I don't know again. So Gian, he mentioned that whenever we pass electric current through a conductor, it attracts other materials. That means magnetic effect. It will show magnetic effect. Okay, but nobody believed on his theory. He actually published in the paper. newspaper he published in, but nobody believed in his theory. Then again in 1820, a mathematician or a physicist we can call, I don't remember, Oersted. Okay, he mentioned that whenever you will pass electric current through a conductor, electric current through a conductor, it will have a magnetic effect. It will show magnetic effect. Okay, and somehow that time people were more knowledgeable or more accepting things, and they accepted his theory. But they both did it separately. Okay, he never cheated. Oersted never cheated. Like this theory was Gian's, and he cheated on that. But yeah, first time it was known in 1820. Okay, that whenever you pass electric current through some conductor. Conductor, what do you mean by conductor? That, yes. What do you mean by conductor? Please, someone.
Sorry, any material which can pass current through it.
Yeah, that means flow of charges. Yes, allow flow of charge. Okay, all right. Any material that allows flow of charges, like metals. Metals are really good conductor. Okay, all right. Understood or not? So this experiment was confirmed by Ampere. Have you heard of Ampere? A-M-P-E-A. What's the spelling of Ampere? Can you please tell me?
Yeah.
Please tell me what's the spelling of Ampere?
AMPERE.
A-M-P-E-R-E. Are you sure?
Yes, sir.
Okay, fine. So Ampere confirmed this with a law called swim law. Okay. Now, what is swim law? Let's understand what is swim law. It is there in your book, but I think it is named after Oersted. Okay, but it was this way you can remember. See, if you pass, like if you have a needle, okay, let's say there is a needle. Okay, it's a needle, and this needle is made of, let's say, a north. This needle is from, you are passing current in this direction, south to north direction. Let's say this is a needle made of magnetic material, which has south pole this side, north pole this side. From south, okay, and you are passing current in a coil. This is a coil. In this direction, you are passing a current in this coil. Okay, so plus minus, that means current will flow in this direction. Fine. So if you pass a current in this direction and keep the needle over the coil, okay, if you are keeping the needle over the coil, what you will see, the coil will deflect in this direction. It will deflect in west, towards west. The needle will deflect towards west. So that's what the meaning is. So how do we swim? Is it swim law only, right? Let me just check once. Let me confirm. I've forgotten a lot of things in magnetic effect. These things, the thing is, nobody is going to ask you. I'm just giving you for information how you can remember this. Okay, so please excuse me for that if I forgot. So it is called Ampere's swimming law. First thing is that. Okay. Now, if you have a magnetically charged needle which has south and north pole like this, and you keep this needle above the current carrying conductor, the needle will always deflect towards west. right? This side will be your west, right? And this side will be your east, isn't it? Yes or no? If this is north, this is south. See, if this is your north, this is your south. So this side is east and this side will be west. Yeah. So Oersted never showed that it has magnetic property. He just showed that it will deflect. The needle will deflect. Okay. That doesn't mean, means he never concluded that it will be having magnetic effect. We are only concluding that if the needle is deflecting, that means it is having a magnetic effect. All right. So this is called swim law. Why do we have to write the swim law? Huh? Not swim law. I don't think it's swim law. It is snow. Sorry. It is called snow. S-N-O-W. This is swimming law. Why it is called swimming law? I'll just explain you. See, the thing is, suppose a person is swimming in this direction. Let's say Atish is swimming like this. Okay. Atish is swimming like this. All right, in this direction from south, and he is swimming from south to north. Okay, that means south to north he is swimming, and he is swimming above water. Let's say this conductor is water. Okay, this current carrying coil is water, so he is swimming above. So above the current carrying coil. Now the current is passed from south to north, towards south to north. What will happen? Atish will always deflect towards west. That's what the meaning of snow is. South to north, when you pass current and you keep above the conductor, you will always deflect towards west. That's what the meaning of Ampere's swimming law is. Understood? I think you can remember this, right?
Yes, sir.
South to north,
Above.
and O means above, oh, sorry, over the conductor, and deflects towards west. Understood? I think it is easy to remember snow. Is it?
Yes, sir.
Okay. Okay. Now let's come to Biot-Savart law. There was another physicist named Biot-Savart. Biot and Savart. Do you know about Biot-Savart law? What do you mean by Biot-Savart law? See, it just means Biot-Savart, they explain that whenever there is a current carrying coil, let's say this is a current carrying coil, and current is passing in this direction, in this coil. This coil can be wrapped like this anywhere, right? Like that. I'm not drawing everything. I'm just trying to show you this much. So it shows that if there is a current carrying coil, so the magnetic field, so magnetic field is represented by B. Okay. So according to Biot-Savart law, dB, change in magnetic field, okay, is directly proportional to the current passing through it. Number one. Number two, change in magnetic field is directly proportional to the length of conductor dl. Right now we are considering only this part, this much length, okay, small length. This length we are calling dl, okay. And we are, let's say we are calculating magnetic field at this point, okay, at point P. So because of this current, there is a magnetic field at point P, okay, and that, let's say from this conductor, it is at some angle. Let's say this angle is theta. Theta is not 90 here, by the way, okay. So the change in magnetic field is directly proportional to the angle or sine theta, okay. And let's say this length is r vector, so it is also proportional to inverse of r square, okay. You remember this inverse square law? We have studied that in gravitation, that gravitational force is equal to gmm upon r square. Remember, F is inversely proportional to r square, remember? Also in electric field is also inversely proportional to R square, electric force. Magnetic force is also inversely proportional to R square. There is something else that we have studied, which is inversely proportional to R square. What is that we have studied in previous chapter? Electromagnetic force, remember? Remember? No? In previous chapter, we have studied no electromagnetic force,
Yes, sir.
electric force. Which law was that?
Sir, it was.
Ampere's law, is it?
Yes, sir. Yes.
Tell me, which law was that? I want to know whether you guys even study at all or not. Current electricity we have studied, na? Coulomb's law, remember?
Yes, sir.
So what is this? F is equal to what? Electric force is equal to what? Remember? No. See, in Coulomb's law we have studied electric force is equal to the force due to actually electric field 1 by 4 pi epsilon naught Q1 Q2 upon R square. Remember? Now do you remember? We have studied that. I don't know whether you guys write this in your notebook or not, but yeah, we remember. So in Biot-Savart law, see, this means directly proportional. See, when we write X is directly proportional to Y, and this means inversely proportional. X is inversely proportional to Y. Here the Y. Here the meaning is as Y increases, X will also increase. As Y increases, X will decrease, right? That's why it is called inversely proportional. Now, if you combine this, you can write dV is proportional. Let's write here dV is proportional. You can write vector symbol just to mention that it's a vector quantity. Is proportional to I dl, change in length, sine theta upon R square. Now to remove this proportionality sign, we will put equality sign and put a constant K. I dl sine theta upon R square. Okay, and this K is equal to what? Do you know what this K is? Yes or no? It's fine. See, K is mu naught. It's a constant. K is just a constant. Q mu naught upon 4 pi. Okay, this is called mu. Okay, this symbol is called mu naught upon 4 pi. And this value is 10 to the power of -7 Tesla meter per ampere. Okay, or you can write like that, Tesla meter per ampere. Now, what is Tesla? What is this Tesla? See, mu naught. First, let's understand what mu naught is. Mu naught is permeability. It's called permeability of free space. What do you mean by permeability? Do you know what's the meaning of permeability? Huh? It's an English literature word. Permeability means, see,
Sir, it allows.
Yeah, yes, exactly. Say it.
It allows something to pass.
Yeah, something. See, in this case, it is magnetic permeability, you can say. Magnetic permeability. That means how much the material will allow magnetic field to pass through it. Okay. Understood? Like a pipe, water will flow in pipe, but if there is some jam in this pipe, it will resist, right? It will resist. The water will not pass fluently. Okay, the water may not pass fluently. So then the permeability of that pipe will decrease. So permeability means how much it allows magnetic field lines to pass through it. That's what magnetic permeability means. Okay, of free space. All right. So this is your Biot-Savart law. Understood? This is your Biot-Savart law. So magnetic field, or we can again we can write it as magnetic magnetic field, change in magnetic field is equal to mu naught upon 4 pi into I dl sine theta upon r square. Okay, understood? And in this is just the magnitude. If you want to write a scalar quantity, scalar. See, I'm not writing scalar because you will think like this is a scalar quantity. Magnetic field is a vector quantity. So let me write in terms of vectors. This will be equal to mu naught I upon 4 pi dl vector cross r vector upon r cube. Okay, this is how it is written in magnitude plus direction. Okay, this is what Biot-Savart law is. Understood? Now, this B is your magnetic field line, magnetic field, or let's write strength of magnetic field. Okay, I is the current, obviously electric current. Mu naught I have already written. 4 pi value you already know. dl is the length of conductor. That's right, L is length of conductor. R, what is R? The distance, or you can write displacement, where from conductor where we are calculating the magnetic field, the strength of magnetic field. Okay, that is B. Understood? Yes or no? Now, what is the SI unit of units? Let's write unit of magnetic field line. So whenever I writing V vector, that means strength of magnetic field lines I'm talking about. Okay. So what's the unit? So the SI unit is Tesla. Okay. SI unit is Tesla, and you can write S as T. All right. Do you know any other unit of magnetic field? Huh? Anybody of you, do you know any other unit of magnetic field? No, right? Okay. See, this is your SI in CGS. What is CGS? CGS is centimeter gram second. Okay, in CGS it is called Gauss. Okay, and represented by G. So 1 Tesla is equal to 10 to the power of 4 Gauss. All right. Now also there are some units of this, that is Tesla. 1 Tesla is equal to 1 Newton per ampere meter. That is also equal to 1 volt second per meter square. That is also equal to a lot of units are there. So let's not write all. I'm just giving you. V is your volt. Okay. A is ampere, N is Newton, S is second, M is meter. All right. Now there is another one unit that we don't usually use it. The 1 and 2, the CGS and SI is used a lot. Mostly we are going to use CGS. Sorry, SI unit. Oersted. The first person to name this. Oersted is OE we represent. So 1 OE is equal to 1 dyne per Maxwell. Okay. Okay, just is Maxwell is again a mathematician who gave a lot of theories about electric and magnetic field. Okay, dyne is the unit of, this is unit of force in CGS. Okay, in CGS unit of force is called dyne. In SI, unit of force is called Newton. Okay, so these are the units of magnetic field. Understood? Yes or no?
Yes, sir.
Yeah.
Yes, sir.
So see, I don't know how much you are getting it because you are not seeing anything. So Biot-Savart law just give the magnitude. Biot-Savart law gives the magnitude and direction of magnetic field lines. Biot-Savart. That's why we have to study Biot-Savart law. This is some copper, let's say copper wire. Okay, so there are wiring in your home, right? Wiring in your home. So how do you know that the wire has some flaws? Like if I say, let's say this is your room. Okay, this is your room and there is wiring all over, right? So inside the walls, there are wires passing by, isn't it? And the current is coming from somewhere, isn't it? Yes or no?
Yes, sir.
Inside it, that's how you can blow bulbs and some switches and everything is there. So how do you know if something burn away or there is some flaw? Let's say the circuit breaks here, there is some flaw. So how would you know that there is some flaw here? There is something wrong with the, why you are not able to switch on fan or something? What, how you will know? Huh?
Burning smell will come.
Louder.
Burning smell will come.
What?
Sir, he said burning smell will come.
Burning? No, not. See, the thing is, even if burning smell is coming, you won't know from where it has burned. But it's not. See, burning smell is because we put a plastic cover over it, right? So it is because of that. It's not because of the wire. Okay, the wire, it won't have that much strength. Ki burning smell will come from inside the wall. Okay. See, the thing is, even a technician, let's say a technician will come. So what he will do, he don't know where the wire has broken up, right? Where the wire is broken. Of course, he is not going to dig up all your wall, right? It will again cost a lot. Then why in the first place we are putting inside the wall if something is going wrong? See, what he will do, he will have a compass. Okay, that has north and south pole. Okay, so what will happen if he will place his compass everywhere, here, or galvanometer nowadays. So what will happen? See, magnetic field. See, whenever a current is passed in a coil, okay, whenever there is a current in the wire, it will create a magnetic field around it. Okay, magnetic field around it. So when you place compass, it will show some deflection, right? We studied here. See, it will show some deflection. Where is it? This. It will show deflection, right? That's what we have studied here. Using Snow law, it will have some deflection when a compass is placed over a coil. So in this case, what will happen? The compass will deflect, but suppose the wiring is breaking, there is a break in wire here. So what will happen? There will be no deflection. When you put the compass here, the compass will show no deflection. So we will understand, okay, the flaw is here. Somewhere the wire has broken this point. Now this point will be dug up and it will be fixed. Okay. Understood or not? See, a current carrying coil will always show magnetic effect. Understood? Read this statement properly. Whenever you pass a current through a coil, it will create a magnetic field around it. Understood? Yes?
Sir,
See, if you guys not respond, sir, believe me, I'll end the call. Okay? I don't care much. If you are not responding, there is no meaning for me to teach here. You'll have to respond. Otherwise, why are you even in the class? Just leave the class. If I'm showing I'm putting a lot of energy to teach you here. At least respect that. When you are writing something in your exam, you expect your teachers to give you marks, right? That time also, I think you should appreciate them to check your notebook and to correct your notebook all the time. Don't do this. See, whenever you, let's say there is a conductor, again, it is there in your book. Let's say there is a conductor, okay? Let's say a copper conductor is there and you are passing current through this wire. You are, I'm not going, okay, let's draw it, it's fine. So plus, minus. Which direction the current will flow, Atish? Atish,
Sir,
what did I ask?
which direction the current is moving?
So answer it. Don't ask me again.
Positive to negative.
What?
Positive to negative. Positive to negative.
Positive to negative, right? From in this direction.
Yes, sir.
Okay, good. So the current will pass in this direction. Let's say I current is, let's say, passing in this conductor. Okay, so what will happen? It will create a magnetic field around it. Okay, and that magnetic field will be concentric circles. Okay, so something like this. Okay, in this direction, it will create a magnetic field. Now, this will help you understand the magnetic field lines. And this will followed by right hand thumb rule. Right hand rule. Okay, that means if you place your thumb in this direction and remove your move your finger, if you put your right thumb in the direction of current, let me write right thumb in the direction of current, and then you fold your fingers. So the tip of your finger will give you the direction of magnetic field lines. Understood this part? I'll show you a animation. Like right now, the current is flowing in the upward direction, right? So you put your right hand thumb in this direction and you rotate your finger. You will see you are rotating in this direction, right? Your fingers, isn't it? So this will be the direction of your magnetic field lines. Okay, and it will be a concentric circle. Center will be here. Okay, I'll just pause and show you one example based on this. Okay, I'll just share my screen from my laptop. Just a moment. See, understanding this is important. Then only I'll stop sharing from here. Okay. I'll share the screen. Okay. Let's see if you guys are able to understand. Can you see this?
No, sir.
Something is wrong. Just a minute. Okay. Now I'm sharing it. Can you see this? Huh?
Yes, sir.
Okay. So this, see, if you here you see you are rotating finger in this direction, counterclockwise direction. You are keeping your thumb here, right, in the upward direction, isn't it?
Yes,
You
sir.
place your thumb in the upward direction. See here. You are placing your thumb in this direction, the direction of current, and you are rotating your fingers. So that rotation gives you the direction of magnetic field. See? Let me give you another one. Okay, what is it? See, this one as well. Can you see this? See here. Isn't it? Can you see this? If current is going in the upward direction and you place your right thumb in that direction, if suppose current is going in downward direction, what will happen? Yes, what will happen if the current is going in downward direction?
Magnetic field will go in the opposite direction.
Okay, I'll stop sharing and I will start again class here. Can you see the screen? You can see the screen now, right?
Yes, sir.
Okay. See, now suppose, see, when we were passing current in the upward direction, so you are getting magnetic field in this line, in this direction, right? Like that. At this point, the magnetic field is like that. But if you are passing current in the downward direction, let's say I here. So the direction of magnetic field line, it will change from this direction, from here to here, like that. Okay, I'm just showing you direction. Understood? Yes? Got it?
Yes, sir.
Now, see, actually, it is really tough. How can I say? See, this is a 2D graph, a 2D paper, right? Or 2D screen that we are watching. So it's really tough to create this in 3D, right? This is really tough to create in 3D. But if you look into your page number, in your book, page number 127, I think. Yeah, so there is magnetic field due to current carrying straight conductor. So there you can see the direction of magnetic field line. I think it has been depicted well here. So you can check that. Okay. Now what will happen? Now this at this point there will be magnetic field lines, right? B1, let's say this is B2, and B1, B2 will remain constant. whatever value of B1, B2 is, it will remain constant. Okay, understood? And this B1 and B2 can be calculated using the formula B is equal to mu naught I upon 4 pi. And what is the distance? Let's say this distance is R1. So you can divide it by R1. Okay, so DL vector cross R vector upon R cube. Right, so 1 R1 cube. So this method you can calculate. So this is your dB vector. Okay, we will you understood now how a current carrying coil will have magnetic field. This is the strength of magnetic field, and this is how it is calculated. So even if suppose the coil is in this direction, right? See, when I'll come to your class, I will tell you. See, here you can see if the conductor is in upward direction, current is going inside, right? Current from this side, it is coming out, and this side it is going inside, right? Can you see this? This circle is perpendicular to this plane. Like if you make this plane like this, the current is going in this direction. Understood? See, suppose this is the circle, so current is going either inside or outside. Now you understood? Yes or no? See, if the current is flowing in this direction, sorry, I, so the magnetic field will be like this at this point. Okay, in concentric circles. First, this is for this point, maybe for this point, the field will be like this. Okay, and the direction will be this. Which direction it is? This is your counterclockwise direction. So when the current carrying coil is going upward, current is going in the upward direction, so magnetic field will be in counterclockwise direction. Okay, and when it is going downward, obviously it will be clockwise direction. Okay, when you are looking from top. That means from here you are looking. Okay, this is your eyes. Understood? Understood this part or not?
Yes, sir.
Okay, so using Biot-Savart law, let's use Biot-Savart law. Use Biot-Savart law. So what do we use Biot-Savart law for? So first, suppose there is a current in infinite conductor. Suppose the conductor is of infinite length. In this conductor has a length L is equal to infinity. Okay, so before this, let's forget this. Magnetic field in a finite conductor. Magnetic field due to a finite length wire. Okay, finite length wire means, let's say the length is fixed. Suppose this is the length of the wire. So how much will be the magnetic field? Let's say here at this point. What will be, let's say you are passing a current I. When you are passing a current I, magnetic field will be going inside. Okay, and inside is represented by, sorry, something is going inside, it is represented by dot. Sorry, inside, not outside, it is coming outside. Outside is represented by dot. And inside is represented by cross. So when the current is going in the downward direction, magnetic field will be like this. So it is going in this direction, magnetic field line. So here it is coming out, right? Coming out of this screen. So this is represented by, this can be represented by dot. It is going now here, it is going inside the screen. Okay, and it is represented by cross. So here you can write cross, here you can write dot. This is how we represent magnetic field lines or anything. And why the cross and dot? It is because of the arrow. See, arrow is usually like this, right? So when you see the arrow from here, from this view, you will only see this point, right? Dot. So that's why when it is coming outside, it is written dot. When you look the arrow from behind, you will see this cross. That's why we are writing cross. When it is going inside, we are writing cross. When it is coming outside, we represent it by dot. Okay. Okay. So so there is a wire of finite length, and you are finding, let's say the current is going in upward direction. So this side, let's say you are finding a magnetic field at this point. So at this point, the magnetic field will go inside the screen. Let's say, and this angle, this is perpendicular. Okay, this dotted lines. Dotted line does not actually exist. This is the length of conductor L, and current it is carrying I, and this distance, let's say this distance is D from this point. Okay, and this angle is, let's say, θ1, and this angle is θ2. So the magnetic field, strength of magnetic field at point P can be written as is equal to, what will be this magnetic field? It is given by mu naught I upon 4 pi d, okay, into sine θ1 plus sine θ2. All right, this is how we calculate magnetic field, strength of magnetic field at point P. Okay, so this is the point P where we are calculating the strength of magnetic field because of this wire, current carrying wire. Understood?
Yes, sir.
Okay. Now do one problem. Sorry. Suppose the length of the wire, it is carrying current I, and the length of the wire is, let's say, L. L is the length of wire. You have to calculate magnetic field at point P. This will be cross because the wire it is carrying current in the upward direction. So now you are given this angle. You are only given θ1 and θ2. So θ1 is given 60 degree and θ is given 30 degree. θ2 is given 30 degree. Find B. You know the formula for B? B is equal to mu naught I upon 4 pi d. Of course, d is the length, this length. Let's keep it d. See, those values not given, you just write in terms of variable. Okay, into sine θ1 plus sine θ2. That's it. Find out and tell me. Got the answer? See, just need to substitute the value of theta 1 and theta 2. Theta 1 is 60, theta 2 is 30. So you just substitute it. So B at point P will be equal to mu naught I upon 4 pi D sine 60 plus sine 30. Right? So this will be equal to mu naught I upon 4 pi D. Sine 60 is how much? Sine 60 is how much? Root 3 by 2 plus 1 by 2. 30 is 1 by 2. So you just write root 3 plus 1 by 2. So this will be B at P will be equal to mu naught I upon 8 pi D into root 3 plus 1. Okay, Tesla. Please write the unit Tesla. Okay, or you can just write T. Okay, now do one more problem. Now suppose this is your current carrying coil I. Okay, let's change the direction of current. Okay, current direction is here. Again, you have to calculate. Now see, since current direction is changed, so now it was going outside. It was it was going inside. Here it is coming outside. The current is coming outside. So that's why dot at point P. At point P, current, this length is L, this distance is D. Okay. So this point you have already calculated. Now calculate at this point Q. What will be the B at Q is equal to what? Find the strength of magnetic field at point Q. Find out. Got it? See, you just need to substitute the values, right? So we know B is equal to mu naught I upon 4 pi D, the length is D. Now what is the angle here, right? So we need to find theta 1 and theta 2. So at this point, this angle theta, this is 90 degree. So there is no theta 2. That means theta 2 is equal to 0 degree, right? Theta 2 is 0. So what will be theta 1? Huh? How much will be theta 1? We don't know it actually, right? So theta 1 value is not known. So theta 1 is unknown, or theta 1, let's write theta 1 itself. So it will be sine theta 1. That's it. Okay. Understood? Or theta 1 how can we find theta 1? So sine theta in this triangle will be equal, sine theta 1 will be equal, this is theta 1. So sine theta 1 is hypotenuse upon, how do we find? Perpendicular upon hypotenuse, L upon H. H will be L square plus T square square root, right? So we can write, instead of this, we can write mu naught I upon 4 pi D, and sine theta 1 will be L upon square root of L square plus T square. So this will be at point Q. Understood this part? Because theta 2 is 0, so sine theta 2 will also be equal to 0. So we don't need sine theta 2. Since we have only sine theta 1, so from this triangle, we can find theta 1, sine theta 1, right? So sine theta, we know sine theta is perpendicular upon hypotenuse or opposite upon hypotenuse, whatever you want, you can say. And perpendicular is your length. This is your perpendicular, P. And this is your hypotenuse, H. Isn't it? H, how can you find? Using Pythagoras theorem. So that will be all for today, and we'll meet again in next class. Okay. Thank you. Bye. You understood or not, Atish and Vignesh? Okay, I'll end the class now. If you are
Yes,
not.
sir.
Okay, we'll meet again in next class. Bye.